So up until this point in this course, we've used trigonometry to solve right angles. In other words, if I were to give you a triangle, and let me actually fix this triangle a little bit just so it's a little easier to see. If I gave you a right triangle, we would use one of these non-right angles, something like theta here, to say, all right, this is my opposite side, this is my adjacent side, and this is my hypotenuse. And we'd evaluate trigonometric functions by looking at the ratio between any one of these three sides. Now, what we're going to do is we're going to start looking at what we call oblique triangles, or triangles that have, or I should say, don't have a right angle. So what an oblique triangle is a triangle that, so triangles that don't have a right angle. And here's an example of an oblique triangle right over here. So you'll notice here that none of these angles are 90 degrees, and so we call this an oblique triangle. And in order to solve an oblique triangle, we are going to need three things. And one of these three things has to be a side. So we have to at least have one side in order to solve an oblique triangle. And I'll just write this and underline that, any two other parts. So to solve an oblique triangle using trigonometry, we're going to need at least, at a minimum, one side and any two other parts. And by parts, I mean either other angles or other sides. And there are a couple of ways that we can do this. And today we're going to start by discussing what we call the law of sines. And the law of sines says, given two angles and any side, if we're given that, or if we're given two sides and an opposite angle. I'll underline the word opposite. So let me just kind of draw these out so we can see these two scenarios. So if we were given an oblique triangle, and what we were given, and let me do these in different colors, we were given any two angles. So these are my two angles, and any side. So it could be this side right over here, it could be this side right over there, or this side right over here, any one of the three sides and two angles. So this is what we call an angle side scenario, or an angle side case. Or if we were given an oblique triangle, and again, we have two angles, or excuse me, two angles, and the side that we're choosing, or that we're given, I should say, is the side that is in between these two angles. We call this an angle side angle case. And let me just quickly highlight this. The side that we have that I would say is in between these two angles, we call this an included side here. We call this an included side. And the reason we call it an included side is because this is the side that is included in trying to create that angle. And in forming that angle, we notice that this side here is the side that is included in both of those angles. So we call that an included side. So kind of go back here. So if we're given either an angle side case or an angle side angle case, these are both examples of being given two angles in any side. The other case where we might use the law of sines is when we're using what's called an SSA case. Let me draw that out. So an SSA case is when we're given two sides. So for example, I'm just going to arbitrarily just choose these two sides. But the angle that we're choosing can't be an arbitrary angle. The angle that we're given has to be an angle that what we say is opposite one of these two given sides. And when I say opposite, I mean an angle that is literally just across from the side that's given. So if I were looking at this side here, the angle that is opposite of that would be this angle here. So we could be given that angle, or, oh, let me just go back on that, see if I can erase this without erasing everything else. Nope, doesn't look like that. So we could be given that angle, or I'll just do this in a different color. We could be given this angle here, because this angle would be opposite of this side. So anytime we're given two sides and an opposite angle, we would call that an SSA case. SSA case. And order doesn't really matter that much. So if you want to flip it around, whatever you want to do there, you can kind of see where that's going. All right. So anytime we're given either an AAS, angle, angle, side, angle, or an SSA case, then we're going to apply something called the law of sines. And the law of sines effectively says that the ratio of any side over the sine of its angle is equal to the ratio of any other side and over the sine of its opposite angle. This is called the law of sines. And I'm not going to go through a full proof of this right now. I will link a proof to this in the description below. But effectively, the proof of this, it's not overly rigorous. It just essentially involves dropping an altitude somewhere in the opposite angle and setting up a number of different trigonometric ratios using the sides and their opposite angles. So if you're interested in that, I will go ahead and include that in the description below. But again, it's not too bad. But I want us to focus on understanding when to use the law of sines, what it says, and how we can use the law of sines in order to solve an oblique triangle. So we can see here, if I were given anything like, for example, this particular oblique triangle here, what we're saying is that the sine, and I'll try a different color here, the sine of this angle A, the sine of angle A over its opposite side, side A, is proportional or equal to the sine of, let's say, sine of angle B over its opposite angle B, or side B, I should say, over its opposite side. And that is proportional to, say, the sine of angle C over its opposite side, side C here. So what we're saying is all these ratios are equal. That is to say, these ratios are proportional to one another. So the law of sine says we can leverage that bit of information to solve for any other sides or angles that we don't know, provided that we are given this information. We're given an AAS, an ASA, or an SSA case. Now you'll notice that I've written that law of sines in two different ways here, and this part really isn't that important, but whenever we have the sides in the numerator, that just means we're solving for sides. Whenever we have our sine of our angles in the numerator, that means we're solving for angles. And again, it just would be one extra step just to get whatever we want in the numerator. So it's not a huge deal, but if you are so inclined, you can set this up from the get-go to set up whatever you want to solve for. One quick thing that I should note, that in this video, I'm going to specifically focus on an AAS and an ASA case. The SSA case is what we call an ambiguous case. And I will discuss this in our next video lesson because it requires a little bit more conversation. So this is something called an ambiguous case, and in the next video, I will go over this more in depth. So let's use the law of sines right now just to solve a given oblique triangle. So let's start with the first example. And I am giving you the fact that this is an AAS case. But let's just pretend for a moment that we didn't know that this was an AAS case. Let me just kind of go ahead and white this out. Let's just pretend we didn't know that for a second. Because often what you would see in a problem is you'd be given a triangle and it would be up to you to determine what is our given information, determining what type of case it is, and therefore understanding which law we would have to use. Because there is a law of sines, as we're going to discuss in a minute, but in later problems, we'll have to use something called the law of cosines. So let's just kind of categorize what we know here. We've got two angles, so we definitely know it's an angle-angle case. Now we need to think about what side we have here. And looking at this, we've got angle C, angle B. Looking at the side that is given, we're given side B here. Ask yourself, is this an included side? In other words, is it a side that is in between these two angles? or is it an opposite side? And hopefully you were able to determine that this is an opposite side. Side B is opposite of angle B. It's opposite of angle B. Therefore, this is an AAS case. So we have an AAS case based on what we're given here. And we would have to understand, all right, because it's an AAS case, we're then going to have to use the law of sines. So let's set this up. So I'm going to write out the full proportion here. You don't have to always write out the full proportion, but I'm going to do that since it's our very first time doing this problem. So again, it doesn't matter how we set this up. I'm going to just set up side A over the sine of angle A, which I don't know, is equal to side B, which we say is 27.4, over the sine of angle B, which is 28.7 degrees. And then next, we would say this is equal to side C, which is unknown, but we know it's opposite of the sine of angle C, which is 102.3 degrees. So from here, you can set up any one of these proportions to solve for any unknown information. Let's just go ahead and start with angle C, just because we at least know, side C, because we at least know what angle C is. So I'm just going to go ahead and box this just to indicate I'm going to focus on this for now, and I'll stay in red. So let's just solve this proportion here. 27.4 over sine 28.7 is equal to side C over the sine of its opposite angle, 102.3 degrees. So I'm going to go ahead and bring this down here, and we're just going to go ahead and cross multiply, right? So we're going to say side C times sine of 28.7 degrees is equal to 27.4 times the sine of 102.3 degrees. And you can just go ahead and set this up and pretty much just divide everything out now. So I'm just going to go ahead and do that. So I'm just going to say all of this is over the sine, what do we say? The sine of 28.7 degrees. So we're going to say C is equal to all of this. So we're looking at that here, and at that point, we can just go ahead and punch this into our calculator. I'll give you a moment right now to try that. But when we actually put all that in, you should get C is approximately 55.747. And let's see if they gave us any particular unit. They did. Oh, they did. They said it was in feet. So we're going to go ahead and write that side C is in feet. So I'm going to go ahead and box this to indicate this is my final answer for side C. But you'll notice that the problem just said find the remaining angle and sides. So we figured out side C, so we're good with that. So what we're missing now is side A and angle A. Well, let me switch to a different color here. Fortunately for us, angle A isn't too bad at all. Angle A is simply what we would need to find is angle A, we could say is 180 degrees minus the other two angles. So minus 102.3 minus 28.7. And you can use a calculator, but actually if you just do this quickly, you should see that angle A is 49 degrees. So I'm going to go ahead and box that as well. So angle A is 49 degrees. So we just got that by subtracting the other two angles that we do know from 180. Just using the triangle sum theorem. Now, finally, we just need to find side A now, and that's where I'm going to use this proportion here. Okay, so side A, we're going to say, all right, side A, which is A over the sine of angle A, which we just figured out below, which is, I'll just write that here, 49 degrees. We just got that in our previous step. And that's equal to, now at this point, you can choose either this ratio or this ratio for this, because if A is equal to B, then A is, and B is equal to C, then A is also equal to C. So it doesn't matter which ratio we choose. I'm just going to go ahead, and this is something that I recommend too. Always try to go with the ratio that is given to you. If I were to use the one with C, you'd be pretty close. But remember, this side C that I'm using right now is an approximation. It's an approximation for what we think side C is, and it's very, very close. But it's always a better idea to try to use the exact sides and angles if we're given that. So I'm going to go ahead and use B. So we got 27.4 over the sine of 28.7 degrees. And again, if you just set up that ratio for me and you went right into what A is equal to, I would be fine with that. Just make sure you understand how you were getting there. We're going to just cross multiply. We're going to multiply sine of 49 degrees by 27.4 and divide it by the sine of 28.7. One thing that I also would recommend in doing these is when we're entering this into our calculator, try to write the side length first, because if we write sine of 49 degrees times 27, depending on your calculator might multiply this angle 49 by 27.4. So it's always just a better idea just to write your side lengths first. After doing some number crunching in your calculator, you should get to A is approximately 43.06 feet. So that is our side length there. And if we were given 3 parts, meaning 2 angles and a side, then we just needed to find the remaining angle and the 2 other sides. So here we just use the law of sines in an AAS case to find all the remaining sides and angles. All right, let's do one more example now. Let's go ahead and look at an ASA case. And again, in this problem here, we know that we're given an ASA case because of the given information. We are given this angle here. We are given this specific side. So we have AS. And the third thing that we're given, and at first it may not be super obvious, but we can say that this angle here is also given to us because we know it's 8 additional degrees to a 90-degree angle. So altogether, this would be a 98-degree angle. So if you haven't already done so, pause the video and read through the problem so you know exactly what the situation is. So we should see that we have a pole that is tilting towards the sun at an 8-degree angle from the vertical, meaning from the vertical, it's leaning 8 degrees away from that toward the sun. So we would be able to say that the sun is right over here. So there's my little sun, all right? And it casts a 22-foot shadow. Please make sure you understand how shadows work, right? In order for the shadow to be over here, then the sun would have to be behind it, right? So if that doesn't make sense to you, go stand outside or something during the daytime. Hopefully you're watching this during the day and not at night. You will not see your shadow at night. All right, so the angle of elevation from the tip of the shadow to the top of the pole is 43 degrees. All right, so the angle of elevation, which we discussed in the previous chapter, from the tip of the shadow, so this right here is my shadow. So from the tip of the shadow to the top of the pole, we have an angle of elevation of 43 degrees. What the problem is asking for is the length of the pole, or how tall the pole is. So this is just basically an oblique triangle. It's an ASA case because we're given 2 angles. So look at the 2 angles that I've drawn in purple. We're given 2 angles, and the side that is given to us is an included side. It is between those 2 angles. It is not opposite either one of the 2 angles. So we call that an included side. ASA case, we're going to use the law of sines. So I know that I need to solve for side A here in my triangle, or the length of that pole. So side A over the sine of 43 degrees, right? And I'm choosing 43 degrees because that is the angle that is opposite of my side, which represents the pole. So A over the sine of 43 degrees is equal to, and from here, I want to use the side length that I do know, which is going to be side C. We know that that is 22 feet. The one issue is I don't know what my angle C is, but fortunately it's pretty easy to figure out. We can say that angle C, which is this angle here, angle C, is simply 180 minus the 2 other angles. So minus 98, minus 43. So if we add those up and subtract from 180, I believe, yes, you should get 39 degrees. So angle C is 39 degrees. So we can put that here. So we've got our ratio set up. From here, we can just say that A is equal to 22 sine of 43 degrees all over the sine of 39 degrees. Punch that into your calculator, and A should be approximately 23.842 feet. And we should probably write that in a very short sentence, just to indicate we know what we're saying and what we just found. The pole is approximately 23.842 feet. Okay, so here was another law of sines problem that involved using an ASA triangle to solve for, in this case, one other side that we wanted to figure out.